Welcome to another exciting edition of HL Chemistry Flipped Classroom. What I want to talk to you about today is something very, very exciting. This glass of water right here. Now, I know your mind's probably already blown, but let me ask you this question. What is it that's keeping this water in this glass right here? This is obviously billions and billions and billions of water molecules in here. What is keeping the water in this glass as opposed to just flying all around the room? And it's tempting to say gravity. A lot of people want to say that, but then what about the oxygen in the room? What about the CO2 in the room? How come I can't hold the oxygen together in this glass like this in a liquid state? What's causing that? So to look at it another way with some of my fancy diagrams here, we've talked about covalent bonds, which is what's holding the oxygen to the two hydrogen atoms. That's what's holding the water molecule itself together. But if you think about it, since the water's staying in the glass and it's staying in a liquid state, there must be some forces of attraction between the water molecules, and that, ladies and gentlemen, is what we're going to be talking about today. So, I know you're stoked. Get your popcorn ready. It's going to be good, and we're going to talk about some intermolecular forces. So let's really just break it down. Intermolecular forces. Again, we've discussed covalent bonds. These are the forces within a molecule that hold it together, that hold the oxygen to the two hydrogen atoms, or in any molecule. These are called intramolecular bonds, like within a molecule. Intermolecular forces, which from now on I'm going to probably call them IMF, are the forces between neighboring molecules. So, like for instance, the intranet is a collection of computers within the same building, within the same high school or whatever. That would be an intranet, whereas the internet is between different buildings. Or an interstate is a highway that travels between states, usually. And IMFs are really important because they influence a number of physical properties, including melting point, boiling point, solubility, things like that. We're going to talk about it at several different points of the year, so it's really important to understand. And very, very key that we get the difference between intra and inter. So we'll look at these animations twice, and then we're going to talk about, this is Adam Sandler playing a character called Bobby Boucher from a very old movie called The Water Boy. Maybe you've seen it. But suppose Bobby uses his special water boy powers to break all the intermolecular bonds in a glass of water. If he did that, what would he have at that point if he could somehow do that? Think about that for a second. If you break intermolecular bonds, here you go, he's going to zap it, and boom, all you're really doing is you're separating out the water molecules. Now, you don't need special water boy powers to do this. You just need a little bit of heat. But he's going to go from liquid water to water vapor there if that happens. So that's intermolecular bonds. He's breaking those bonds between the water molecules. In the liquid state, they're nice and close. And then when he breaks the intermolecular bonds, they're in the gas state. But still, notice H2O. Nothing's changed about that. Now, suppose instead of breaking the intermolecular bonds, he breaks the intramolecular bonds in a glass of water. Then what would he have? Think about that for a second. Now, if he did that, this is much harder to do, but he would be breaking those covalent bonds, and then he would actually be causing a chemical reaction, a chemical change. He'd have oxygen gas, which would be here, and hydrogen gas, which would be there. So, totally different thing. Much more difficult to do. It can be done with electricity, but you've probably never seen it happen. One thing to keep in mind is that intramolecular bonds are much stronger than intermolecular bonds, and that's something to keep in the back of your mind as we go through and talk about this. So basically, the main thing that intermolecular forces influence is boiling point. The weaker or the less attracted two molecules are to each other, the easier it is to separate them and the lower the temperature at which something will boil. One thing to watch out for is oftentimes, because we're so conditioned to think about water, we think about boiling as something that happens at a high temperature. That's not necessarily the case at all. Nitrogen's boiling point is negative 200 degrees Celsius. So when we think boiling, don't bias yourself towards water. But anyway, materials that have very low intermolecular forces, like nitrogen, there's very little attraction between one nitrogen molecule and another, tend to be gases at room temperature. a term you'll hear thrown around in IB quite a bit is volatility, which is the tendency of a liquid to become a gas. So things that become a gas easily have high volatility. Water is considered to have low volatility, but there are other liquids that have lower boiling points and are considered more volatile. So just a term I needed to throw in there and introduce to you and that you will see. So there are some different types of intermolecular forces, and one of them we call it dipole-dipole forces. And all that really means is we've already talked about dipoles. Polar molecules are going to be attracted to each other because they have a partially positive side and a partially negative side, and opposites attract. So, for instance, in HCl, the partially negative side, which is the HCl, is going to have somewhat of an attraction to the partially positive hydrogen that's in another HCl molecule next to it. So, inter between molecules, and all this force is observed in all polar molecules. Another type of IMF is called hydrogen bonding. Now, this happens in a very specific circumstance. It happens when hydrogen is directly attached to nitrogen, oxygen, or fluorine. So we have a hydrogen atom bonded to an oxygen atom, like in water, for example. So basically what happens is nitrogen, oxygen, fluorine are the three most electronegative elements. They have a very strong attraction for electrons, and if you think about hydrogen like an H2O, it only has one electron and one proton. So you're kind of pulling that electron away from hydrogen. You're leaving basically an exposed proton. These little details, we don't need to know a ton about them, but I'm just trying to explain to you why hydrogen bonding works. So for example, if we're looking at two water molecules here, so we have these shared pair of electrons in the covalent bond. Oxygen is going to tend to hog those, and then again, hydrogen is just one proton and one electron. And so when you start to like pull its electron away from it, you're just basically leaving that proton kind of sitting out there, out in the open. And so that can form a pretty strong attraction between this hydrogen and an oxygen in another water molecule. Now again, it's much weaker than the actual covalent bond, but it's a fairly strong type of intermolecular force. So let's talk about a last type of intermolecular force. But first, let's just kind of think about something that's kind of bizarre. It actually is possible to have liquid helium. You have to get it very, very cold, negative 269 degrees Celsius. That's nearly absolute zero. But if you do get helium atoms that cold, they will actually form a very interesting liquid that does all kinds of crazy things. Like it's possible for it to climb out of the container that it's in and leak through glass and things like that. But that's a story for another day. But just the idea of, like, if we think about it, how could helium ever exist as a liquid? You've just got these helium atoms. What kind of forces are ever going to come into play to hold those together? So I'm going to try to explain it to you with some wonderful and very, very complicated and fancy little animations that I've made. So here we have our helium atom. Here's our helium nucleus, 2 protons, 2 neutrons, and we've got 2 electrons. Now, of course, what's happening normally is these electrons are just kind of whizzing around the nucleus, kind of going everywhere, but if you can imagine kind of pausing time for a second, or just through pure happenstance, it's possible that the electrons would just happen to be on one side of the atom. And if they are on one side of the atom, that is going to create what we call a temporary dipole or a temporary polarity. And I'm talking just for a moment in time. Now, under normal circumstances, normal temperatures, this really isn't going to make any difference at all, because in a helium balloon or in helium in the gas state, the atoms are way too far apart for this to matter at all. But if we cool helium way, way, way down, what starts to become important is the helium atoms slow way down and they start to come nearer each other. And what can happen is since there is a temporary polarity in this helium atom, if there's another helium atom over here, well, opposites attract, like charges repel. These electrons now are going to be attracted a bit to this temporary polar helium atom, and that's going to create a polarity in the neighboring helium atom. That's called inducing a dipole. So over a large enough collection of helium atoms at a cold enough temperature, this can add up to something significant. Now, it is a very weak force because these electrons are only existing this way momentarily, and then they're going to continue, zipping along like they were doing before. But in the case of helium, at a cold enough temperature, negative 269 degrees Celsius, molecules have a small enough kinetic energy that this can actually is just strong enough to hold them together in the liquid state. So this is called London dispersion forces, sometimes called just London forces. That's why the dispersion part is in parentheses. These are very weak forces of attraction caused by temporary polarity in atoms or molecules. I mean, more often molecules that we're going to be talking about. And this is where, like I just showed you, we have temporary dipoles that induce a dipole in a neighboring molecule. You can kind of get this whole shifting back and forth effect that can provide just enough of an intermolecular force to cause things to be, like I said, to form liquid helium. Now, as we'll learn in larger molecules, it's more significant. But, I know I've been smacking you in the face with this knowledge here. This is chemistry knowledge here. This is you at this point. And I know it's a little tricky, but we'll talk about this more in class, and we'll see if we can wrap our brains around it a little bit better. So let's kind of summarize what we've talked about in terms of intermolecular force and think about their strength. I just finished talking to you about London dispersion forces. This is the weakest of these intermolecular forces, and it's the only intermolecular force that nonpolar molecules are capable of doing. Polar molecules can engage in a stronger force. These are permanently polar molecules. They can do dipole-dipole forces. And then the strongest IMF is hydrogen bonding, found in specific polar molecules where hydrogen is directly attached to hydrogen. Hydrogen is directly attached to oxygen, nitrogen, or fluorine. It's basically an extreme version of dipole-dipole. So something that is doing hydrogen bonding is also doing dipole-dipole forces, and basically everything can do London dispersion forces. So they can be kind of nested in that way, if you will. What's critical to remember is that all of these are much weaker than covalent and ionic bonds. So intermolecular forces by nature are much weaker than intramolecular forces. So I brought this up. I'm gonna mention it now, that strength of intermolecular forces, and actually London dispersion forces, is influenced by molar mass and really the sheer number of electrons. So for example, if we consider our diatomics chlorine, bromine, and iodine. Now, if you ponder for a second and think about these are all diatomic nonpolar molecules, so they can do London dispersion forces, and that's it. But they're right next to each other on the periodic table, vertically, I mean. Chlorine is a gas at room temperature, bromine is a liquid, and iodine is a solid. So chlorine has the weakest of the intermolecular forces of the three, bromine kind of medium, and iodine the highest. And the difference between those, or what causes that, is just the greater molar mass and the greater number of electrons in iodine compared to chlorine increases the strength of the London dispersion forces, so it's going to increase both the melting and the boiling points. So definitely something to bear in mind as we go and continue to talk about these things. Another thing, and this is kind of weird, it's called van der Waals forces, and it kind of depends. I've seen different definitions and different ideas about what van der Waals forces actually are. I've heard them, being used equivalently to London dispersion forces, like synonyms. But what matters for the purposes of IB is what IB says they are. And what IB says they are is a collective term that refers to London forces or London dispersion forces, dipole-dipole forces, and dipole-induced dipole forces. Now, what are dipole-induced dipole forces? Doesn't really matter because for some reason they're in this part of the syllabus but not in other parts. But basically, sort of like how we were talking about inducing a dipole from a nonpolar molecule, except a polar molecule inducing a polarity. Again, it doesn't matter that much. So it's what you should look at it, view it as a collective term that can refer to all types of intermolecular forces except hydrogen bonding, basically. So that's what IB says van der Waals forces are, and that's what we're going to go with. Now, something we're going to have to do, and this is rather challenging, is looking at things and rank them by their boiling point. And what makes it challenging is you really have to put a lot of stuff together that we've learned. But hopefully what we're able to do is just look at these different substances, you'll be able to roughly list them. Oh, this would have the lowest boiling point, and this would have the highest. Now, there's definitely some complexity to it and a lot of factors. I'm not going to go over it. We're going to go over it in class, not on this workbook. or not in this video, but in your workbook, approximately page 94, the workbook changes from year to year. There'll be a whole page of kind of notes on this, and I just want you to point that out to you here, so that this is something that definitely goes along with this topic, and something we'll be talking about in class. But it's worth maybe mentioning in your notes that further information can be found in your workbook, I guess, and you can figure out the exact page number, I think. Okay, so shifting gears just a little bit is how something called solubility relates to this. Solubility is how well things mix or dissolve into each other. And the famous phrase that's used here in chemistry is like dissolves like. And what that means is the more similar two things are, the better they mix together. If they're very dissimilar, they don't mix together. So things that are polar, substances with polarity, will mix with other polar substances, whereas nonpolar things will mix with nonpolar things. But if you mix and match that, they don't mix. So polar mixes with polar, nonpolar mixes with nonpolar. But if you try to combine, for instance, a polar liquid and a nonpolar liquid, generally they separate. And the more similar they are, the more confident we can be that two things will mix together. So, for example, water not only is polar, but it can do hydrogen bonding. So water mixes really well with polar substances, especially polar substances that are small, like water is, and can hydrogen bond. And the more dissimilar to that, the less likely that water is going to mix with it. So, the classic example, really, if you think about it, of things that don't mix is water and oil, oil and water. Oil is non-polar, and water is polar, like I said. And if you try to combine them, they separate into layers. I'm sure you're familiar with this and you've seen it. Even if you stir it up, these things are eventually going to separate out again on their own. So we'll talk about that and develop some of those ideas a little bit more, but just kind of remember the phrase like dissolves like. And I think that's it, folks. Thank you for watching. Be sure to ask me questions if you have a next class, and we will continue to talk about this stuff. Thank you very much.